Sara Snogerup Linse. This year's prize is for engineering proteins. Can you tell us what are proteins?
Yes, I like that question. Proteins are molecules, rather large molecules that you find everywhere in your body. They conduct almost all the processes that go on, the memory, the thinking, the coagulation, the muscles. They are really the workhorses in our bodies.
So they are so plenty, why to produce even more?
If there are so plenty.
Why do you need to produce even more?
Yeah, because in the body, some of the proteins we have or other organisms have are enzymes that speed up chemical reactions. But there are reactions we want to do in chemical synthesis or to produce fuels that those enzymes can't do, so we have to improve them.
This is about enzymes produced by Frances Arnold this year.
Yes. That's the one half of the prize, and that is to make the enzymes conduct new chemical reactions or better the reactions they do today. And the other half is about improving binding proteins. So these are proteins that attach to something and conduct biological processes by this means, for example, antibodies. And this technique can then be used to produce human antibodies against pathogens or other substances.
And to come back to the main method in both prizes, so to say, used, you were talking about evolution. And when we think about natural evolution, you think it's often described as a combination of chance and necessity. Is this what they did?
Yes, so this is, I would say, a combination of chance and necessity, but also quite a big element of thinking, because what they have done is to really speed up the evolution. Because nature has had billions of years, but now you want the process to be possible in maybe a few weeks or a year or something in the laboratory.
So it was like random experiments and then picking up the right parts of it?
Yes, I would say in nature it's a rather random process because the mutations happen by chance, maybe due to UV radiation or something. Whereas in the laboratory it was a combination of knowledge base. So you have to have some idea of which positions to vary, but then you add a randomness on top of that.
So the biggest difference would be that you know what goal you have.
Yes.
While in nature, actually there is maybe no goal.
I guess I would say nature has no goal, but what works, works, and everything that makes things better or that you can populate a new niche is then kept. Whereas in the directed evolution, the scientist defines the goal. I want to break this bond or make this bond, and I want to make it as quickly as possible at 58 degrees or whatever is the condition. Yeah, so the scientists define the condition.
And one of the prize laureates, Frances Arnold, she knew she wanted enzymes. Why couldn't she design them from the beginning?
It's a very good question, and scientists also try to do that. And in principle, we know which kind of intermolecular forces operate in proteins, but I think the problem is that it's a multi-combinatorial problem, so it's still not possible with the knowledge-based methods today to design an enzyme from scratch. One can design enzymes that have some catalytic efficiency, but to really, really get somewhere, you have to bring in the power of evolution to optimize them.
Can you tell us something about who is Frances Arnold?
I think she is a very good and a very talented scientist, a very curious scientist, and also goal-oriented. She knows what she wants to do, and then she sets out to do it.
And she made it.
She made it, yes.
Also, the other prize laureates, George Smith, he designed a method, this phage display, which is really hard to understand what it is, but it's a method to produce antibodies.
Yes, it's actually a method. So the way he designed the method, he took those phages that are these protein capsids that have the DNA inside that codes for making the capsid. And what he did, he put in the gene for the protein he wanted to study, and he then sort of fooled the phage to put it on its surface. So this is what we call phage display, on the top or on the bottom, depending on how you turn them around, but at the tip of the phage. Yes, and I think the key element of his technology that really made it fly was this physical linkage between the gene and the protein product, so that you could fish out phages and then take out the DNA and work further with new generations of variations.
And then Gregory Winter used it to produce antibodies. What is special about antibodies?
The special thing with antibodies, I mean, it's a part of our immune defense. These are proteins that nature have designed to have a possibility to become very specific. So the phage technology harnesses that power. Antibodies have 6 different loops in each binding pocket that it can vary. And this is ideal, in fact, to put on a phage and do random mutagenesis to search for very high affinity antibodies. So they can have very high affinity and high specificity for a certain molecule and not react with others.
And then they can be used to make drugs, actually.
They can be used as drugs because they can either bind to objects or surfaces we have in the body, or they can bind to things that would try to invade us.
How many drugs have been produced from this method?
I actually don't know, but I know that of the 15 most sold drugs on Earth, 11 are made by this method.
Are they very expensive?
I'm sure they are very expensive, but the advantage with the phage display is that you can derive antibodies with such high affinity, much higher than you get with immunization, that you can lower the doses. You can use much lower doses, you can even use them cutaneous on the skin, you don't have to inject them. So there are many advantages with them.
So what do you think is next? What is the vision for the future?
The vision for the future, I think we're just at the start. I think we will see many more enzymes that catalyze bonds that we had no clue that an enzyme could actually do. One of the latest examples from Arnold's lab are enzymes that catalyze the formation of carbon-silicon bonds. And these are bonds you don't find in nature, and there is no natural enzyme, but she managed to take one and evolve it to form these kinds of bonds that are important for making materials, for example.
New materials.
New materials, yes.
Thank you very much, Sara Snogerup, Linse, for being here with us. Thank you.
Thank you.